Swayam Prabha. Digital India. Educated India.
Hello, good afternoon. Welcome to the course on comprehensive view of speech processing. Today's lecture is 13th in series, and today we are going to discuss about the frequency domain processing of speech signals. So far we discussed under the processing of speech signals. So we discussed about like how do capture the speech signal. Then afterwards how to digitize the speech, then from the once you represent the speech, then the next step is to like how do we characterize the speech, like how do you visualize or how do you identify the different properties in speech signal. So in that actually we discussed about the theory of LTA system, concept of LTA system. And in that, as we know that for the LTA system, the output response can be computed using convolution of input and the unit sample response of a system. So in view of that, we discussed about the LTA system and we introduced the concept of convolution. So as the convolution we introduced, so along with that we also mentioned about a similar concept known to be correlation. Used to analyze the similarity between a pair of signals. So we in the last class we discussed about both convolution and correlation. How do we like interpret the process of convolution and correlation using a graphical way? Given the two discrete sequences, how do we compute the correlation and convolution? And along with that we also discussed about the complexity, computational complexity of evaluation of convolution and correlation between the two sequences. So today as I mentioned, today we discuss about the frequency domain processing of speech signal. So in that we are introducing the topic of discrete Fourier transform. So before going to the details of that, there is a small topic left over under the correlation. So that we first will cover in first 5 to 10 minutes, then we move on to this. So here related to the correlation, the important concept known to be autocorrelation in view of particularly the speech signals. So here we know that the correlation means it is between two signals, right, and we will try to see that how those two signals are related, whether they are similar or dissimilar or whether they are orthogonal. So those things we can able to analyze using correlation. And here the concept of autocorrelation is nothing but just analyzing the correlation between or analyzing the similarity between signal and its shifted version, whereas in case of normal correlation we will take a pair of signals, one signal will fix and then other signal will be shifted, and each time for every shift we will try to see that what is the overlapping area between the two signals, and then that overlap area will be viewed as the correlation at that particular shift. And whereas here in case of autocorrelation means we have a signal and the second signal also happens to be the same signal, but it is shifted version. So in view of that, you can see the autocorrelation formulation will be R of n is denoted by the autocorrelation for the given sequence x of n. So we can write it as x of k into x of k plus n, where k varies from minus infinity to plus infinity. And here x of k plus n will provide the different shifts. If you vary the value of n towards positive, then we are shifting the signal x of n in the positive direction, and if you are varying the n towards negative, it means we are shifting the x of k towards in the negative scale or the negative direction and all. So here let us see in case of autocorrelation function, it has very important properties, particularly its in view of speech we will discuss the autocorrelation to analyze the the periodicity of a given signal and all, periodicity of a given signal. So, here let us I just draw a small segment of a speech consists of 4 cycles. Here you can see here it is a 4 cycles, a segment of 4 cycles of speech signal, and on this if you perform the autocorrelation function, then you can able to see the autocorrelation function something look like this. You can able to see the autocorrelation function something look like this. So, here you can see the x axis will be the shift, like the amount of shift, and the y axis gives you the y axis will be like r of n. That means, for every shift what is the value of r of n, like when n equals to 0 what is the r of n. So, this value is nothing but r of 0, then afterwards we have r of 1, r of 2, r of 3, r of 4 and so on, and here again this peak corresponds to r of capital N, and again this peak corresponds to r of capital 2 n, and this is r of 3 n, likewise r of minus n, minus 2 n, minus 3 n and so on. And here the important property here is that if you perform an autocorrelation on a signal, if the signal is periodic, then its autocorrelation function or its autocorrelation sequence is also periodic. Autocorrelation is also periodic, and here in this autocorrelation signal you will find the maximum value when the shift equals to 0. When the shift equals to 0, that means autocorrelation means signal and its shift. That means the correlation, or you can say that the similarity between the signal and itself, signal and its shifted version. When shift equals to 0, it means nothing but you will get a maximum correlation, because the same signals are both are exactly same. So, you will get a maximum correlation and both are similar. So, you will get a maximum value, and this is known to be r of 0. It is nothing but the energy of the signal, because if you evaluate when you put n equals to 0, it is nothing but x of k multiplied by x of k square. It is nothing but just multiplying just taking the square of the each sample of a signal and summation across all the samples. It is nothing but the total energy of the signal, So, that way you can see that the maximum autocorrelation you can observe when n equals to 0, and as you proceed, as you shift the signal further either in positive direction or in negative direction, the amount of correlation will be decreases, obvious, because here you can see in this example x of n you have 4 periods are there. So, when you perform the autocorrelation when n equals to 0, you have a complete overlap from 0 to 4n, 0 to 4. So, the moment once you shift one of the signal and the other one you make it a static, and other one the other x of n will be shifted, x of 1 plus n. So, it means that now at that time you have a overlap of only like 4n minus 1 samples, because already one sample will be shifted. So, here the static signal at x equals to 0 you have a signal, and whereas the shifted version you do not have a signal. So, therefore, you have an overlap between only like 1 to 4n, 1 to 4n. So, that means 4n minus 1 samples have overlap. So, as you proceed further, if you shift further, then the sample overlap will be decreased. So, the area under the two signals will be decreases. So, you can observe the decrease in value. But here one important property of autocorrelation function is that if the signal is periodic, you can able to see a periodic signal in the autocorrelation is also periodic, autocorrelation signal, because autocorrelation is also a signal, because this is also a sequence, R of n is also a sequence, it is also a signal. So, if you plot the signal, you can able to see periodicity in the autocorrelation function, because that is intuitive also. You can able to see here you have a signal here, right, you have seen this like for example, you have for example, this is your signal, right, and so if you perform the without 0 shift, then it is nothing but multiplication of signal by itself. So, therefore, you have a maximum correlation, and if you shift the signal, for example, if you shift the other signal, right, and then it continues here. So, when you shift the other signal, you can see here as you move on here we shifted the another signal by n, right. Here this is 0, then this is n, 2n, 3n and so on, like this is 4n, right, and you are shifting the the same signal and you can able to see that at you can, by shifting by a period, exactly period, then you can able to see a proper overlap, right. You can see where, because this since it is a periodic signal, other than just if you shift by just a sample shift, shift by other than the periodic shift, you can able to, you see that the samples between the two signals are not properly aligned. So, you will get a decrease in the sample amplitudes. That means, for example, if you look at, for example, if you see this way, actually here I have not plotted this signal, it is not a periodic one. So, but actually if you shift this signal unevenly, then here it may have a higher amplitude here, but the other signal may have a very low negative value. So, if you take a product of that, the resultant will be, you will get a very less value and out. And again, if you have a proper alignment like this one, if you shift the other signal by exactly by one period, then if you take the overlap, and you can able to see that whatever the sample amplitudes here and here also the both the signals have the same sample amplitudes, having the same polarity. So, if you take the like the overlap area between that, you will get the slightly higher value, but here this value will be lesser compared to 0th shift, because at 0th shift we have exactly the signal and its the other signal which is a 0 shift, it is nothing but we have not shifted at all, it is nothing but there is a complete overlap and all signals, all samples have both the signals have same polarity, you will get a maximum value. The moment once you disturb, once you shift the other signal, one of the signal, then the polarities will change, and then the multiplication of sample amplitudes, you will get lesser value, and again you will get somewhat maximum value, higher value, but not at this at the higher value at a 0 shift, but you will find a somewhat significant higher value when the shifted signal exactly shifted by one period or 2 periods, 3 periods, like integer multiples of periods. If you shift it, then you can see a part of the signal has lot of overlap, part of the signal has overlap, and for both of them the samples have same polarity, you will get higher value. That is what you can able to observe from this. Here you can see at the 0th shift you have the maximum amplitude, and afterwards the correlation value will be decreases, and again you can able to observe a somewhat higher value. You can able to see somewhat the other signal shifted by exactly one period, you can able to see maximum value, somewhat higher value. Then afterwards again the periodicity will be disturbed, because the signals are not properly overlapped, so polarities will be different. So, therefore, you can have the signals having the correlation having a lower value, and again you can able to see somewhat significant higher value at the shift of 2n, and again at the shift of 3n, and so on. So, that way you can able to see that in case of autocorrelation function, the autocorrelation sequence is periodic, but it is not exactly periodic. You can see here, because here periodic means the same replica, the same pattern has to be repeated, but here the peaks are different, right. But if the signal having like stretched infinitely, then in principle then you can see that autocorrelation sequence is also periodic, perfectly periodic. So, this property, this autocorrelation function property, this will be used, exploited in speech signal to estimate the periodicity of a given speech segment, because we know that the speech is a non-stationary signal, right, and so therefore we will analyze the speech frames at a rate of 20 to 30 milliseconds, and in that 20 to 30 milliseconds speech segment we will take, and then we will compute autocorrelation, and we will look for the periodicity. And if the autocorrelation function we observe the periodicity, it means that the chosen speech segment or the considered speech segment for the evaluation of autocorrelation is a periodic one. Say we say that it is a voiced speech segment, and suppose if we do not get any periodicity, if we do not observe any periodicity in the autocorrelation function, autocorrelation sequence, it means that the segment that was chosen from the speech signal is like unvoiced segment, because it is a kind of a noisy one. So, you do not find a periodicity, so you do not find the periodic nature of autocorrelation function. So, that way this autocorrelation function phenomena will be used for estimating the periodicity. From that we can detect whether the speech is a voiced segment or not, and from that we can also get an idea that the excitation is from the vocal folds vibration or from the other excitation like unvoiced excitation. So, for that purpose the autocorrelation function will be used. Anyway, the details of this one we will discuss later when we discuss about the time domain parameters of a speech signal. At that time we can parameterize the speech by using this autocorrelation analysis. So, we will see the details more in the later. Right. Actual topic of today's discussion, that is a frequency domain processing of speech signal. As we know that in a time domain we can able to see certain details such as the amplitude fluctuations in the periodicity of a signal, and with that we can detect whether the speech is present or not. So, such details you can able to observe from the speech signal if you display or if you analyze in a time domain. But if you want to like analyze, or if you want to characterize the speech, or if you want to determine what are the dominant frequencies or frequency components that are present in a speech segment, are nothing but the resonant frequencies of a particular speech sound if you want to analyze. So, in that case if you look at or if you observe the time domain speech signal, we do not get any information from that. So, for that purpose we need to represent the speech, or we need to transform the speech from time domain to frequency domain, and from where you can able to observe the frequency components present in a given speech segment, and in that the frequency components, like which frequencies attains the significant energy, and that way we can able to locate or we can able to determine the formant frequencies or the resonant frequencies of a given speech segment. And so, here actually we are not going to the details about this Fourier transform relations, but actually here I just mentioned, I just want to I just gave the expressions for estimating the Fourier transform. And first actually here you can see the first pair of relations, they are known to be like a continuous time Fourier transform CTFT. It means if the signal is in time domain, or if it is a continuous domain or analog domain, then how do you compute the spectrum, or how do you compute the frequency domain representation of a signal. And similarly, if the spectrum is also continuous, and in that case how do you estimate or how do you compute the recover the time domain signal back from its frequency domain representation. So, here these two relations, or this pair of relations, are known to be a Fourier transform pair in continuous domain. So, known to be continuous time Fourier transform. So, x of t is your continuous time signal, and from by knowing x of t, by using this expression integral minus infinity to plus infinity e power x of t into e power j omega minus j omega t dt. So, here since x of t is continuous, so therefore, here we use the integration for computing the Fourier transform, and e power minus j omega t dt integration over that, and you will get x of omega. And here the x of omega is also continuous, that means the spectrum whatever you observe here is also continuous. So, from this spectrum to recover the signal back x of t, we use the inverse Fourier transform. So, you can see x of omega into e power j omega t d omega, because here from the spectrum we need to retrieve or we need to recover the signal, time domain signal. So, using this expression we can able to recover the time domain signal from its spectrum. So, these two are known to be continuous time Fourier transform relations. And but actually here, since these are continuous in nature, both the signal as well as its spectrum, we cannot handle with the machines, we cannot process with the machines. So, as we know that the machines can able to process a finite sequence, a finite number of samples with a finite amplitude levels, right. So, therefore, here we cannot handle the continuous time signal. So, therefore, we need to discretize that. So, my x of n is here is a discrete time signal. So, for that if you apply a Fourier transform, since x of n is a discrete, because the signal is not present continuous, it is not present all the time, only at the instants time specific time instant the signal is present. So, therefore, this integration formulation will be replaced by the summation, like n equals to minus infinity to plus infinity x of n e power minus j omega n, e power minus j omega. So, with that you can able to compute the spectrum, or you can say that compute the Fourier transform for a discrete time signal. So, we will get x of omega, and here in this evaluation, even though the signal is a discrete time signal or a discrete signal, but if you try to compute the spectrum, you will get the spectrum is happen to be continuous. You will get the spectrum, for a discrete time signal, if you observe the spectrum is still continuous. So, therefore, if you want to recover the discrete signal from its spectrum, so since the spectrum is a continuous still, so therefore, by using this expression like so we will see that why you have taken this minus pi to plus pi. In the next slide it will be clear to you, because here for a discrete time signal, if you compute a spectrum, you will get the spectrum is observed to be periodic. So, since the spectrum is periodic, that is the spectral content of a signal, original signal is repeating. So, therefore, here if you process one period, it is good enough to recover the discrete time signal and all. That is the reason that we taken minus pi to plus pi integration over x of omega e power j omega. But here, even though the time domain signal is a discrete, but its spectrum is still continuous. So, you cannot handle the continuous spectrum. So, therefore, and here these pair of relations are known to be discrete time Fourier transform relations, discrete time Fourier transform relations. But again, these are also not useful, right. We can able to evaluate this using a computer with a finite discrete time sequence, but still its spectrum is continuous, we cannot handle, we cannot process that. So, we want that both the signal as well as its spectrum both should be discrete, and it means that discrete time as well as the number the amplitudes are also should be discrete. So, therefore, the final transform the pair of relations are known to be discrete Fourier transform, whereas this is the discrete time Fourier transform, here is the discrete Fourier transform, where under the discrete Fourier transform these two expressions, this pair of expressions will provide you the desired spectrum. That means the spectrum is finite and it is also discrete. You can see x of n is a discrete signal, and since it is a finite, so our signal is limited to 0 to capital N minus 1, that is nothing but capital N samples, and for that we are estimating the spectrum x of k for different values of k, So, here since we have n values, so we will get a spectrum is also having n values, right, and from this discrete spectrum we can able to recover x of n also. So, here the discrete Fourier transform, what we observe here is that, so we will get both the temporal signal and its spectrum both are observed to be discrete as well as periodic. So, therefore, it means the same information is repeating in every period. So, therefore, we will take a period of signal here in the time domain and corresponding period of signal in the spectral domain. So, these two are equivalent. So, from that we can have relations between discrete time signal and its corresponding spectra. So, this final pair of relations are known to be discrete Fourier transform relations, and here we can able to achieve that both the signal as well as the spectra both are discrete and finite, So, now but actually here I am not giving the details about how do we derive, how do we achieve this, how do you get these relations and all. So, for that actually there are like you can have the concept, these concepts you can get much clearer if you go through the standard signal processing textbooks, where all these are very fundamental results and all. If you can go through that, you will get a clarity on that. So, why the expressions are like this and how these expressions are arrived. So, all these details you can able to observe from that. Yeah. So, now we will see that like the way we like illustrated graphically the process of convolution, right. We have seen the mathematical expression, how this mathematical expression is evaluated the graphical way. So, that we have seen. Similar to that here also. So, we will look at the interpretation of DFT relations in a graphical manner. So, for that actually here we have taken a time domain signal x of t, continuous signal x of t. It is extended from minus infinity to plus infinity, and assume that if you compute a continuous time Fourier transform, you can observe that the spectrum corresponds to this signal will be something like this, This is just for illustration, I had taken these two signals, x of t is a time domain signal and x of omega is my the Fourier transform of this signal, and so you can able to see like this, and this is also intuitive also because this is a Gaussian signal. So, if you apply the Fourier transform, you can also find the Fourier transform is also observed to be Gaussian, but here the both the time domain and the frequency domain, they are like reciprocal to each other. So, therefore, if the signal is stretched in the time domain, it means in the frequency domain the signal will be like kind of shrink or compressed. So, that kind of reciprocal phenomena can be observed between the time and frequency domains. So, this is my time domain signal, this is my frequency domain, and here the frequency domain also can observe that the omega, that is the frequency components, are present till infinite, the continuous, that means at all the time, that means all the frequencies are present till infinite. So, you cannot handle neither x of t nor x of omega, right. So, therefore, we want the signal to be discrete. So, what we do for the signal to be discrete, we know that. So, if you multiply a continuous signal with a sample train, with a unit sample train, then the result will be a discrete time signal, right, because this is a unit sample train, this is unit sample train, that means here if there is only one sample at 0 with unit magnitude, it is not a unit sample delta of t or delta of n, right. And suppose for example, here you have a unit sample we have a unit sample train where the samples are present at intervals of capital T, right. Then you can write this unit sample sequence as when m equals to vary from minus infinity to plus infinity, delta of, you can write it is not it is a time scale, so delta of t minus mt. It means that if you give different values of m, when m equals to 0, it is nothing but delta t, it is nothing but the sample at t equals to 0, and when m equals to 1, this becomes delta of t minus capital T, it is nothing but the sample at capital T shifted by capital T, and when m equals to 2, the sample is shifted by capital 2 t. Likewise, when m equals to minus 1, minus 2, you have these samples. So, all these things can be represented by expression like summation over delta of t minus mt. This is a sample train, unit sample sequence, and if you multiply this signal, a continuous signal, with this, you can see that wherever the samples are there, at those samples, whatever the amplitude of the signal, so that signal bears, that signal amplitude will be taken by these samples, right, because you are simply multiplying that, these are unit samples. When you multiply this with x of t, and wherever the samples are there, at that point whatever the signal amplitude is there, and when you multiply that, you can see that 1 multiplied by this corresponding x of capital T, you will get that one. So, that way you will get a discrete time signal, which means that now you have continuous signal, now you obtain a discrete time signal. It means that the same signal, but it is present only at the instance, discrete instance, only at t equals to 0, capital T, 2t, 3t and so on, right. Likewise, here also, right. And so, you can see here we have performed a product multiplication of these two. So, therefore, here the expression for this discrete time signal is also x of m into delta of t minus mt, right, over the like m like summation over m. So, this we have seen like in the discrete time signal, if you want to represent by using unit sample, we have a similar expression. We have seen x of k into delta of n minus mk, right, a similar expression we have seen. So, the same thing here also, this is nothing but a sampled signal or a discrete time signal, right. And now you can see that now in the time domain, at least I got a discrete time signal, but still you have a problem here, because even though it is a discrete time signal, the signal is present till infinite. The signal, that means the samples are extended from minus infinity to plus infinity. So, if there are infinite samples, I cannot handle, again the machine cannot handle the infinite samples, right. You should have some finite number is required. So, we will see how to get a finite sample sequence from these. At this time, at least we have a signal transformed from continuous to discrete time. Now, we have discrete time signal is available, and now we will see that. So, what is its impact in the frequency domain? How its what will be the spectrum corresponds to this discrete time signal in the frequency domain? Because we know that for x of t, this is the spectra x of omega, right, and this is my unit sample train. So, for the unit sample train, so if you take a Fourier transform, we know that again you will get a sample train, but here the samples are separated inversely proportional to the separation over here. If the samples are very close part here, then these two are, then here in the frequency domain the samples are very much separated. So, here you can see the samples are separated by T, capital T, whereas here you can see the samples are separated by 2 pi by T, that means inversely proportional to T, right. If the T is very small here, it means the samples are very close, right. T is very small, then in that case here, since it is 1 by T, 1 over T, so the samples are very far apart here. So, that was a property of time and frequency, relation between time and frequency domain. It means in the time domain, if the signal is compressed or the signal is shrinked of the, then in the frequency domain it appears to be like expanded version. So, here in for unit sample train, if you look at the graphically, the spectrum corresponds to this will be something like this. You have again a sample train which are separated by 2 pi by T. So, you can write the corresponding expression for that, because since these are also samples, you can write delta of omega, because earlier it is a T, it is a time domain, now it is a frequency domain omega. So, they are separated by 2 pi by T, 2 pi by T k, where summation k equals to minus infinity to plus infinity, and the 2 pi by T is the sample amplitudes here, right. So, that way here you can see for a unit sample train, again you have a sample train in the frequency domain, right. And now here the time domain, we are multiplying these two signals, we are multiplying the sample train, unit sample train with the x of t, you got the discrete time sequence. So, here in the time domain, if the signals are multiplied in the time domain, and if you apply a Fourier transform on that, and it is equivalent to in the frequency domain, so their corresponding spectra are convolved. It means here we know the other way, if the signals are convolved in the time domain, then if you apply a Fourier transform in a frequency domain, they will be multiplied. That means those two, their corresponding spectra are multiplied. That is what we have seen when you are discussing with the convolution. So, similarly here, but here in the time domain, if the signals are multiplied, or if the signals are like the product of the two signals in the time domain, and if you for the resultant signal, if you apply a Fourier transform, you can see the Fourier transform of the discrete signal is nothing but the the product of the convolution of Fourier transform of the continuous signal and the Fourier transform of the sample sequence. So, now you can see, visualize how the convolution of these two, how it looks like. You have x of omega, and here we have a samples, we have a sample separated by 2 pi by T, right. And if you perform a convolution on that, how do you convolve that? Here both the signals are symmetric. So, you can take one of the signal, right, rotate by 180 degrees. So, if you rotate by 180 degrees, then since it is a symmetrical signal, the signal remains same, right, because it is a symmetric signal. So, therefore, even if you rotate by 180 degrees also, the signal will not change, the signal remains same. So, after rotating 180 degrees, then what you have to do? You have to shift this rotated signal towards positive for a different shift till infinite, and then till again minus infinity you have to shift. And now here you can see there is an impulse over here, there is an impulse unit sample, and now when you after rotating this one, when you shift this signal across the impulse, since the impulse has the magnitude 1. So, therefore, what you observe here is that when you perform convolution between this and this unit this sample train, you can able to see whatever the spectrum is there, x of omega, you can able to observe the replication of a spectrum at each sample location. That means at sample location 0, you can able to observe whatever the spectrum x of omega, it will be there, right. And again at 2 pi by T, again you have a spectrum, and again at 4 pi by T, you have again a spectrum. So, likewise, wherever the samples are present, at every sample, since you are shifting this, so you can get the overlap between this and this will be again the replica of x of omega will be there at either point. So, now you can see there are the x of omega is observed to be present at every sample, right. And so, with that you can see this I have just put it represented as a dotted ones. So, you can see there is a lot of overlap, right, and here the resultant signal will be here. I have plotted like using a red curve. The resultant plot I just plotted with the red curve, because when you look at here this peak, this is the normal peak offered by this particular sample, and this sample also we have this spectra will be superimposed over here. So, because of this spectra, the tail of the spectra will be observed here in this portion also. So, and similarly the tail of the previous this one also will be observed over here. So, if you want to take a resultant of that one, so the peak of this one actual spectrum plus the tails of these two, the adjacent ones, these two and even this also, all of them will be added up and you will get the signal, the spectrum something appears to be like a periodic one, right. You see my actual spectrum is something like this. The moment once I discretize, once I sample this signal, right, x of t to x of n, I got the spectrum is observed to be periodic, and here not only periodic, I lost some information also, because my actual spectrum is like up to extend to infinite, right. But here I can see I got the periodic spectrum, that means whatever is there it is repeating, it is replicating. So, here, so therefore, from this what I can convey is that the moment once you discretize, once you sample the signal, you will lose some information. The spectrum becomes periodic. The earlier the spectrum is not a periodic, but here the once you discretize the signal, once you sample the signal, the spectrum becomes periodic, and not only periodic, but you will have a loss of information also, because all the adjacent tails will be added up. So, with that the true spectrum will be lost, and again this is the problem here, and this problem is known to be aliasing. It means that here the spectral components of the adjacent ones also will be mixed up. So, this is known to be aliasing in the frequency domain, aliasing in the frequency, because you can see the spectrum, this is the actual spectrum, and here because of the periodicity, because of the samples, so you can able this spectrum is also superimposed over here, all these sample tails will be present in everywhere. So, if you add up, then this becomes a distortion. So, that way this becomes a periodic signal and a periodic spectrum, and the original spectrum properties are lost. The original spectral properties are lost, because you can see here maybe at this portion, at the significant portion, the signal sample frequency components are preserved, but other places it will be lost, right. So, this is known to be aliasing effect. So, because of the aliasing effect, the true spectral characteristics of a signal will be lost, But here how do we, because here in this, so how do we overcome this, or how do we reduce the loss? One way is that actually here you can see the loss is because of overlapping of the spectra. So, if you avoid this overlap, or if you minimize this overlap, then we can able to minimize the spectral loss, right. So, how do you minimize that? One way is that actually if you keep these samples apart, far apart, then the effect of the adjacent spectra overlap will be less, right. So, if you want to keep this distance between these two samples very far apart, it means what you have to do in the time domain, we need to sample at a very close rate, that means we need to sample at a very high rate, that means more number of samples have to be done in the kept in 1 second, that means here the sampling rate should be very high, then samples are very close apart. So, therefore, here the samples are very far apart. So, therefore, the overlapping will be reduced here, but that is again a problem, because here the spectrum is present till infinite. So, if you want to like minimize this distortion, it means that the samples should be sampling should be done at an infinite rate. It is nothing but again the same continuous signal will be result, it is of no use at all, right. But depending upon our usage here, even though the signal spectrum is present minus infinity to plus infinity, but here the significant power is present from here to here only. So, this is good enough to retain the spectrum from here to here, and you can able to truncate, or you can able to neglect the other frequency components, that is good enough. So, therefore, here for that, in that case actually, so we will just fix up some maximum frequency, and we will try to retain the frequencies till that point, and so that if you want to retain the frequencies till that point, so accordingly we need to sample that. Accordingly, we need to sample accordingly. It means, suppose if you want to retain the frequency up to omega 1 for example, it means here with the twice omega 1 you need to sample here. With the twice omega 1 if you sample here, then here the samples are apart, so that the still overlapping will be there, but the overlapping is very insignificant and we can avoid that. That is one way to do that. And other way is that actually here, if you want to perform, if you want to minimize this aliasing effect, one way is that you need to increase the sampling rate, but again increasing the sampling rate will require a lot of bandwidth for transmission, and even for signal representation or signal storage also require lot of storage, a lot of memory is required. So, all the issues will arise out of it. So, therefore, here depending upon the frequency of interest, what you can do is that you can able to pass this signal, this time domain signal with an appropriate filter by keeping a cutoff frequency of our desired interest. Then the spectrum will be like here itself, in time domain itself we are removing the frequencies. So, therefore, if you sample the signal, time domain signal with the double that of the frequency of interest, then we can minimize this overlap and this aliasing can be minimized and all. So, therefore, to avoid aliasing there are two things. One thing is that one way is that to increase the sampling rate, so that the aliasing can be, effect of aliasing can be minimized, and second one is that by using anti-aliasing filter, because otherwise the frequency components are like minus infinity to plus infinity, we cannot handle that. So, therefore, depending upon the required frequency, we will pass the signal through a low pass filter, where it allows the frequency components from 0 to till that the frequency of interest. Then afterwards, if you sample the signal with the twice of that cutoff frequency, then we can able to avoid the aliasing. So, this is that filter, usually it is low pass filter, is known to be like anti-aliasing filter. So, first we pass the speech signal or any continuous signal through the anti-aliasing filter, then afterwards whatever the cutoff frequency of anti-aliasing filter, we will sample the signal with the twice the rate of the cutoff frequency, so that the frequencies that are for interest will be retained over here. So, that is the concept of aliasing. So, here the aliasing means, here when you sample the signal in time domain, you can minimizing aliasing. We have two approaches. First thing is that we can increase the sampling frequency, so that the aliasing can be minimized to some extent, or otherwise you can the input signal will be passed through the anti-aliasing filter of the desired cutoff frequency, and so that the frequency of the input signal will be like limited, band limited, and then after that we can sample the filtered signal with the desired sampling rate, so that the effect of aliasing will be reduced over here and all. So, here this is the reason that actually here you can see for graphical interpretation we need to perform the convolution of between these two. So, like for that reason I just we have discussed about the graphical interpretation of the convolution, where one signal has to be fixed and other signal will be rotated by 180 degrees, and then shift the rotated signal, shift the infinite samples that are present in a discrete time signal, which cannot be handled, which we cannot handle that. So, therefore, if you want to get for handling the discrete time signal, you need to convert the infinitely extended discrete time signal to like the finite sample finite discrete time signal and all. So, for that actually again here the depending upon our interest, because if you look at the signal, discrete time signal, here the sample amplitudes are slowly decaying and all, and they are present till infinite. So, suppose for example, if you are interested to have a samples from like this amplitude, and beyond this if you truncate or if you remove the sample amplitudes, assuming that for certain application they are not required, they are not much useful. So, in that case we are retaining the sample amplitude from minus 2t to plus 2t, that means only 5 samples we are considering that. So, how do you remove the other samples and keeping or preserving only the samples from minus 2t to plus 2t. So, for that what we can do here is that we multiply that infinitely extended discrete time signal with this rectangular pulse. And here the width of the rectangular pulse is chosen such a way that whatever the samples that need to be preserved, right, and that is the width of the rectangular pulse. Like here we want to preserve the samples between minus T naught by 2 to plus T naught by 2, minus T naught by 2 to plus T naught by 2. So, in between, in this range we want to preserve the samples, and beyond this we want to remove the samples, right. So, for that reason the infinitely extended discrete time signal is multiplied with this rectangular pulse, so that my so that the earlier infinitely extended discrete time signal becomes finite. You can see now the my discrete time signal is available from minus T naught by 2 to plus T naught by 2. So, now I can able to handle, because this is the finite sequence, you have 5 samples or it may be 100 samples, 500 or 1000 or 10,000 whatever, but still it is finite, I can able to manage, I can able to handle with the machines. So, now my discrete time signal is available, and also my discrete time signal is also finite in nature, I can do that. And now we will see that for converting the infinitely extended discrete time signal to a finite duration discrete time signal, right. So, what we had done, we multiplied the discrete time signal with this rectangular pulse, and now by performing this operation, right, to convert the infinitely extended discrete time signal to the finite size discrete time signal, right, we have performed this operation. We have to see that what is this impact in the frequency domain, what is its impact in the frequency domain. So, here what we have done, again here in the time domain we multiplied 2 signals, like whatever the discrete time signal, whatever is we have derived by sampling process, that discrete time signal is multiplied with this rectangular pulse, then we got the finite discrete time signal, a finite length discrete time signal. And again here these two, the product of 2 signals in the time domain we have performed to achieve this. And in the frequency domain, how it will be. So, again in the frequency domain we know that for a rectangular pulse the spectrum is something appears like this, it is known to be sync pulse, So, if you have a rectangular signal, rectangular pulse, so if you compute a Fourier transform, you can get the output will be like a sync pulse of the nature like a sin x by x form, and here you can see here the rectangular pulse is stretching from minus T naught to plus T naught. So, therefore, here you can get the sync pulse, where here the zero crossing points will be for a major lobe, it will be minus pi by T naught to plus pi by T naught, and this is 3 pi by T naught, and this is 5 pi by T naught, and so on. At regularly you can able to observe the zero crossings, and the amplitude of these peaks and valleys will be slowly decaying as it progress towards to infinite and minus infinite and all. So, this is known to be sync pulse, is the spectral representation for the rectangular pulse in the time domain. And now in the time domain, this rectangular pulse is multiplied with the discrete time sequence to achieve to get this one, to obtain this one. And for this, if you want to compute the Fourier transform, or like in a Fourier domain or in the frequency domain, so what will be the spectrum corresponds to this finite sequence, or this finite discrete sequence, if you want to observe that. So, here in the frequency domain, so whatever the product here in the time domain, here to get this one we multiplied this rectangular pulse with the discrete time signal. So, here in the frequency domain it is nothing but the convolution of the spectrum corresponds to the rectangular pulse with the spectrum corresponds to the discrete time signal. So, we know that the spectrum for the discrete time signal will be a periodic. This is a periodic one, already lossy signal, and we can able to minimize the losses by using either anti-aliasing filter or like with high frequency rate, high sampling rate. So, we need to perform now to get the spectrum corresponds to this finite sample sequence will be like a convolution of this the periodic spectrum with the sync pulse, because in the time domain those two are multiplied, the rectangular pulse is multiplied with the discrete time sequence. So, in a frequency domain, the frequency domain equivalent of this particular signal is nothing but convolution of the periodic spectrum with the sync pulse. And here if you apply this, if you observe the sync pulse, So, here in sync pulse, here the center we have a maximum energy or a maximum amplitude, the frequencies in between these minus pi by t naught to plus pi by t naught, and afterwards the amplitudes or the strength of the frequency components will be gradually reduces. So, when you perform a convolution of these with that periodic spectrum, and again the same process, you can graphically visualize that. You can keep one of the signal is fixed, another signal will be rotated by 180 degrees, but here both the signals are symmetric signal. This is also symmetric. You can see that the spectrum become periodic. My original signal spectrum is not at all periodic, but due to the sampling process I got the spectrum to be periodic. And again on top of that, in this periodic spectrum, again you can able to see the ripples over the periodic spectrum, and here these ripples, you can see the ripples, this is a distortion, this is not present, not there in the original spectrum, but still here you can able to observe these ripples. So, these ripples are due to the convolution of the sync pulse with that periodic spectrum, because in the sync pulse you can able to see the positive and the valleys, the peaks and valleys, right, and alternatively varying and all. So, when you convolve this with the periodic spectrum, you can able to observe the ripples over the periodic spectrum, and this is a distortion. This is not at all present in the original signal, but due to these various operations in the process of sampling, then afterwards making the signal to be finite, you can able to observe these ripples in the periodic spectrum and all. But this is not the one, whatever, this is not at all present in the original signal, but here these are introduced because of these processes that are performed in the time domain and all, and these are known to be the artifacts that are introduced in the process of digitization and all. And here these ripples, this distortion is known to be side lobe leakage or side lobe distortion, because you can see this is the major lobe and these are the side lobes, right. These side lobes is varying like alternatively positive, negative and all, and these introduce a distortion in the periodic spectrum, and these distortions are known to be like due to the side lobe leakage. It means that here the power will be like will be present here, the like negative, then followed by positive, alternative, the strength of the frequency components varies, right, and because of that you can able to observe the ripples in the spectrum and all, and this distortion is known to be side lobe distortion, or this is due to side lobe leakage power, and whereas if you do not have these alternative like variations, then the distortion will be reduced. And here again these two, the relation between the rectangular pulse and its corresponding spectrum, they are again inversely related to each other. Suppose for example, here if you take if the rectangular pulse having a larger width, means in the frequency domain you can able to see a more sharper the major lobe, and again the more sharper side lobe, and here the ripple distortion will be high, higher, right. And this is because of the sudden transition of the rectangular pulse, because you can see in the rectangular pulse at this point, till that we are preserving the sample amplitudes, but here suddenly we are the sudden truncation was there, and because of the sudden truncation you can able to observe the sync pulse is observed to be extended towards infinite and all. And again this width also will matter. If the width is very large here, minus t naught by 2 plus t naught, that means the width is t naught. If the width is very large, you can able to see here the pi by t naught, the inverse of t naught will be observed. So, with that you can see there is a sharper major lobe, and again the sharper valleys that are observed here. That means more sharper sync pulse is observed, and that leads to more distortion and all. So, therefore, instead of using these rectangular pulse, so one may use the different other types of windows known to be Hamming window or Hanning window. So, which are actually here instead of sudden truncation over here. So, they will do a smooth like a smooth truncation, or like a smooth roll off will be there, like a smooth roll off, just it varies something like this. Instead of that, you can have the smooth roll of something like this. So then with that, actually you can see that now because of the smooth roll off, you don't see the sudden sharp these peaks and valleys here. So therefore these are not to be hamming or hanging window, different types of windows. So with that, the effect of the side lobe leakage can be minimized, can be reduced to some extent by choosing appropriate windows. But the problem here is that by using these hamming or hanging windows, the sample amplitudes are distorted. Whatever the samples that we want to preserve, those amplitudes will be reduced, right? You can see, because you are multiplying with the hamming window, whereas here this has unit magnitude. So therefore, whatever the samples that are there within the T naught by 2 plus minus T naught by 2, they are preserved, they do not be disturbed at all. Now because of these sample amplitudes, the original sample amplitudes will be reduced, will be changed, and with that the signal properties will be affected. But here at the same time, here the side lobe leakage effect will be reduced, right. So but here, even though after doing this, my time domain signal is finite, but still my spectrum is still continuous. You can see still it is a continuous, because whatever the periodic spectrum is there, on that periodic spectrum again we convolve with this. So we get a distortion, we get a ripples over here. So this is known to be like a side lobe leakage or side lobe distortion. And but still here again in the frequency domain, it is still continuous, still it is continuous. So we need to avoid that, we want the discrete over here. So that will continue that in the next class. We will stop here at this point of a time. We will continue that, how to make the spectrum also to be discrete. So those things we will discuss in the next class. So we will stop here. Okay, thank you.